let's start. So actually I'll start over there. So first of all, reminder, please register. Even if you're watching this online only, and I know that there are people who do that, please register. It will really help me and the department. Second, so I actually got permission from Jemima to remove my mask, but I'm not sure if she has the authority to give me this permission. So I'm still not removing my mask. I will decide later whether or not to remove it. In my other class, I got permission, but it belongs to a different division. So I'm not sure if I'm allowed to remove my mask. Anyway, let me remind you where we were. So we were in the process of defining the kind of one of the first, not invariant, or at least in the sense that it's relatively easy and relatively powerful, and it's the Jones polynomial. So we start from the Kaufman bracket. The Kaufman bracket is a map bracket from unoriented nodes and links, or more precisely, unoriented node and link diagrams, to the polynomial ring in three variables, A, B, and D, defined by, so the map is defined by two relations. The bracket of a crossing is equal to the bracket to A times the bracket of its zero smoothing times plus B times the bracket of its one smoothing, and the bracket of a, so okay, with this relation you can get rid of all the crossings, so you're left with crossingless diagrams on the plane, in the plane, meaning unions of circles. So the bracket of a union of k circles, in this case k is equal to 5, the side circles may be nested in each other, is d to the 5. And then we ask ourselves, is this really an invariant? To check if it's an invariant, we needed to check invariance under Reidemeister 1, which is the move that says that this is equal to that. Reidemeister 2, which is the move that says that this is equal to that. And Reidemeister 3, which is the move that says that if you have a crossing and another strand underneath, you can slide it to go above the crossing. So we need to check invariance under these three moves. And oddly, the order is 2, 3, and then 1. The good order in which to go through them is first 2, then 3, then 1. So we checked invariant under Reidemeister 2, and it was not invariant. Sorry, not means N-O-T, not K-N-O-T. So, you know, when there is doubt, I'll switch to Danish. So, we found that the Kaufman bracket is EK invariant under Reidemeister 2, okay? But we found that if B is equal to A inverse and D is equal to negative A squared minus A to the minus 2, then the coefficients that make it non-invariant become 0, and it becomes an invariant. So from this point on, B is equal to A inverse as D, and D is equal to negative A squared negative minus A to the minus 2. So therefore the values are no longer in polynomials in A, B, and D, but now the values are in Laurent polynomials, because we have to invert A, in A. So polynomials in A to the plus or minus 1. Okay. Things look bad, because if Reidemeister 2, which is relatively simple, killed 2 of the variables, Reidemeister 3 certainly is going to kill the rest. But in fact, it's not so bad. So let's test invariant under Reidemeister 3. So let's compute the bracket of the left-hand side of Reidemeister 3. So, oh, sorry, I think I want to do it the other way around, not that it matters. So, let's compute the bracket of this. Now, in principle, it's a messy computation, because we have to expand 3 crossings. Each one is 2 terms, so it's a total of 8 terms, right? 2 from here times 2 from here times 2 from here, that's 8 terms. So we need to expand 8 things, and then we need to find, we need to expand another 8 things for the other side. So we're going to write 16 diagrams, and hopefully they will come with the same coefficients. But in fact, it's much cheaper, because we will be lazy, and we will expand only this crossing and that crossing. And we'll see what happens. So, expanding the top crossing, we get that this is the bracket of, so the top crossing becomes a 0 smoothing, so it looks like this, and this passes here, and I forgot the coefficient with coefficient A. And then plus, well, B now is just a synonym for A inverse, but I may as well write B. I could write B just as well. So it's B times the smoothing of that. Sorry, yeah, B times the bracket of the one smoothing. And exactly the same happens down below. So you get A times the bracket of this picture plus B times the bracket of that picture. But you see, this picture is identical to this picture. So these brackets are equal. This picture, by Reidemeister 2, we've already proven Reidemeister 2, so we can use it. So assuming A is B inverse, and sorry, B is A inverse, and D is whatever it is, I can use Reidemeister 2, and this thing here is the bracket of, well, if I use Reidemeister 2, I just get this thing. But this is also that. So these two are equal. So these two are equal, and we're done with Reidemeister 3. We were lucky. Okay? And then it remains to check invariance under Reidemeister 1. And an unpleasant surprise comes. So let's compute the bracket of the left-hand side of Reidemeister 1. So the bracket of this is equal to the bracket of its one smoothing. So in the one smoothing, sorry, 0 smoothing, in the 0 smoothing it gets replaced by this picture, plus, sorry, with a coefficient A, plus A inverse times, wait, did I blunder? This is the zero smoothing is you start at 0 and you turn to the right. Yes, so that's fine. Plus A inverse times the bracket of this picture, and but this picture has a circle in it, and a circle is equal to, so a circle is worth d, and d is negative a squared, negative a to the negative 2. So you get negative, so you get negative, you get a times negative a squared, negative a to the negative 2 times, once you remove the circle, you're left with a straight line. So times a straight line plus A inverse times a straight line, right? Because this is just a straight line topologically. And let's see, A times A to the minus 2 is A inverse, and the A inverse here comes with a negative sign and here with a positive sign, so they cancel, and so you're left with A times A squared, so you're left with negative A cubed times this, and so you find that, unfortunately, the left-hand side is not equal to the right-hand side of the Reidemeister move. This is the right-hand side of the Reidemeister move, and we got an extra A cubed, negative A cubed. So that's bad news. You can solve it by taking A cubed to be a cubic root of negative 1. Unfortunately, you can show that if you take A cubed to be the cubic root of negative 1, you get a trivial invariant. I mean, I will not show it right now, but you don't get anything interesting. But there is a different way around it. So the different way around it is clever. So what you do is you find an invariant whose behavior under the Reidemeister move, one move, is the opposite of that. And then you multiply the two, and the result is an invariant, is a genuine invariant. You find something that doesn't change. Okay? And it turns out that there is a simple thing whose behavior is opposite to this. So let me introduce it very quickly. Okay? So maybe I'll start one step backwards. Okay? So given a two-component link, so we're talking here about knots and links, but I'll start now with a two-component link. So given a two-component link, so if L is a two-component link, there is a simple invariant called the linking number, and the linking number is defined as follows. So first of all, I should have said oriented link. So the Jones is about, the Kaufman bracket is about unoriented knots, but now I'm talking about oriented links. So this is equal to, this is by definition equal to 1/2 times the sum over all crossings, so over all x's, which is a crossing of the two components, So I'm not counting crossings in which a component intersects itself. Okay? Of -1 to the crossing and -1 to a crossing, also known as the sign of the crossing, is defined as follows. So you see, if you have a crossing of oriented strands, it could be one of either types. It could be either of this type or of the opposite type. And let me explain how you tell which is which. So this is a little bit like in electromagnetism, if you've seen that, or in cross products, the sort of sign of a cross product. So basically, you take your right hand and you hold one of the strands so that your thumb is pointing in the direction of the flow, and then your fingers indicate the direction of the other strand. And if you do the same here, then your fingers will be pointing in the opposite direction. So this is a right-handed crossing, or if you wish, this is a left-handed crossing. And since we're prejudiced and biased, we decide that right-handed is 1 and left-handed is -1. Anyone in the room is left-handed? Ooh, 2 people. I am sorry. This was this is it's a standard convention. It doesn't mean anything about. Well, anyway. For example, let's compute the crossing number of, the linking number of the Hopf link. So the linking number of the Hopf link is 1/2 times the sign of this crossing plus the sign of that crossing. The sign of this crossing, well, this is right-handed, so it's 1. The sign of this crossing is also 1. So it's 1/2 of 1 plus 1, which is 1/2 of 2, which is 1. On the other hand, the linking number of the opposite cross-link, Hopf link, so in fact the same link, but let's flip one of the orientations, is equal to, so here each of the crossings flipped its orientation, so you get 1/2 times -1 plus another -1, and that's -1. Now, if we were able to show that this is actually an invariant, then we will in particular prove that these 2 links are not the same, which is news. This is something that we didn't yet know. So we have to show that the linking number is an invariant. Okay? But for this, we need to check invariance under the 3 moves. Okay? So, why is it invariant under Reidemeister 1?
Should just be 0 there?
Yeah, basically, the 2 sides are identical except one crossing, but that one crossing is not counted because we're only counting crossings of the 2 components, and this is a crossing, well, I don't know which component this would be, but it's a crossing of one component with itself. So we get invariance here. Why is it invariant under Reidemeister 2? So now there are choices. If the 2 crossings, if the 2 sides here belong to the same component, then they don't count here and they don't count here. If they belong to opposite components, you just have to check that the sign here is the opposite of the sign here, and they are opposite. So the sum of these two signs is 0, which is the same contribution as you get on the right-hand side. So this is easy also. And for Reidemeister 3, so for Reidemeister 3, it's kind of good to know a general property of Reidemeister 3. So in Reidemeister 3, somehow the crossing don't change, only how they relate to each other change. In other words, this crossing corresponds to that one, right? This and that are the same. Well, I mean, if you just look at the sign of this crossing, it's the same as the sign of that crossing, because if you had removed the third strand, they would simply be the same. Likewise, the sign of this crossing is the same as the sign of that crossing, and the sign of that crossing is the same as the sign of that crossing. So the sum here is equal to the sum here, and we have an invariant. Okay? Okay, that's the end of the aside about the linking number, which, as I said, is an extremely useful invariant. Okay? Well, it separates these two links, for example. But now let's try to do the same for a knot. Okay? So let's define the right of, so this is a new definition, and this is called the right. So the right of a knot, or in fact a link, is the exact same thing, except I remove the limitation that the crossing is a crossing of two different components, of the two components. Namely, I just do the same sum, but without limitation. Okay? And now this makes sense also for knots. Okay? And the argument that we had for why it is invariant under Reidemeister 3 is equally valid. The argument we had for why it is invariant under Reidemeister 2 is also equally valid. But the argument we had for invariance under Reidemeister 1 fails. How does it fail? So let's compute the right of this. So the right of this is, well, actually I didn't even bother to specify the orientation here. In fact, it doesn't matter how I specify the orientation. If I orient this kink going up, then this is a positive crossing, a right-handed crossing. And if I orient it going down, well, I have to hold my hand the other way, but again, it's a positive crossing. So no matter how you orient it, it's a positive crossing. So its right is, oh, sorry, I forgot one thing. I also want to drop the 1/2 factor. So its right is equal one more than the right of that. Okay? And similarly, the right of this, so this is the same, it's the same kink except I flipped the crossing. Okay? So this is now a negative crossing, no matter how you orient it. So this is going to be -1 plus the right of a straight line. And I suppose for completeness, I should have also computed the bracket of the opposite kink in the case of well, the Kaufman bracket. And you can carry out the same computation, and you find that you get -a to the -3 times that. Okay? So, we have one invariant whose failure is additive by adding 1 or subtracting 1, and another one whose failure is multiplicative by multiplying by negative a cubed or negative a to the negative 3. Okay? So clearly if you multiply them appropriately, it will be, you'll get something that doesn't change. So, definition, the Jones polynomial of a link L is defined to be, so the bracket of the link L multiplied by negative a cubed to the power negative the right of k, of L. But now, if I want the right to make sense, I have to take L to be an oriented link. Right? Otherwise, all of these signs will not make sense. And to compute the bracket, I simply forget the orientation. Okay? So this is more or less the definition of the Jones polynomial. But then there are conventions. So first of all, the bracket, every time you compute the bracket, you get at least one cycle. Right? So no matter when you resolve all the crossings, when you smooth all the crossings, at the end you're going to get at least one cycle. So the bracket, so in this d to the power k is always greater than or equal to 1. So the bracket is always divisible by d. And then the convention is to divide it by d. And finally, the Jones polynomial is usually written in terms of a different variable, and that the variable is usually called q. So you take this and you apply the replacement. A goes to q to the power negative 1/4. And that's the Jones polynomial. Okay? We will compute it in a minute, and then you'll see how it comes out to be. Let me add a dot here for reasons that will be clear later. Any questions, any comments so far about the Jones polynomial? Okay. So you see, I promised you that this is a class also about computation. So how do we compute this? So, I want to turn on my computer. Oh my God. It's supposed to turn on by face recognition, and it's having difficulty. Well, I also have a password. So I'm supposed to show you how to compute it on the computer. But the first thing is, how do I represent a knot on the computer? Okay? So there are several possible representations. There are programs to convert between them. Let me show you my favorite representation. So I'll show it by an example. How do you represent the trefoil knot on a computer? So what you do is you choose a starting point and enumerate the edges as you go along the knot. So 1, 2, 3, 4, 5, and 6. Okay? And remember, what is a knot diagram? A knot diagram is just a graph. We talked about it 2 classes ago maybe, or a class ago. A knot diagram is just a graph whose vertices are quadrivalent and have a counterclockwise orientation. So what I will do is I will simply enumerate, or I will simply, for each of the vertices, tell you the cyclic ordering of the edges around it in their cyclic ordering. And by convention, I will start from the incoming lower strand. Okay, so the incoming lower strand is, I'll just mark it with an arrow in each of the cases. This is the incoming lower strand. So, for this crossing, this is the crossing, so I'll use the English letter X to denote the crossing. So this is a crossing between 1, or it's a crossing whose edges around it are 1, 5, 2, and 4. 1, 5, 2, 4. This crossing is a crossing of 5, 3, 6, and 2. So 5, 3, 6, 2. And the last crossing, this one is a crossing 3, 1, 4, 6. 3, 1, 4, 6. Okay? And finally, because this is a planar diagram, I will put a PD around it. Okay? So this stands for planar diagram. Now, from this information, you can recover the diagram. Why? Because, well, you know which one is the, well, for each crossing, you know which one is the, you can recover the graph. You can, for each crossing, you know which one is the incoming lower strand, and then you can tell the orientation of the other strand by seeing whether the other pair of numbers, so one kind of pass-through strand will be 1 to 2, or 5 to 6, or 3 to 4. The other one will be like the opposite, the 5 to 4, or the 3 to 2, or the 1 to 6. And you can tell which way it is oriented by which number comes first and which number comes later. So it's oriented from the 4 to the 5. So you can recover the diagram from this. Good. Let's start implementing. So, I'm using Mathematica, and unfortunately it's a bit of an expensive software. There is a student edition which you can buy on the internet for about $150, and I promise to refund you if you will stay in this class to the end and use it seriously. Okay? Anyway, so let me start Mathematica. Actually, here is, you know, if you look at this, you will see this brown line, not brown, gray line here. This gray line here actually represents a part of the program that's hidden. Let me briefly unhide it. So I'll select it, go to Cell, go to Properties. Can you see this? Mm-hmm. Or should I go to a higher magnification? Higher magnification, fine, 150%. Is it better? You know what, I'll go even higher, 200%. Okay, so let me again go to Cell, Properties, and Open. Now it's an open cell. So, and you find that the hidden cell here is a list of knots. For example, the knot called 3, 1, so it's the first knot with 3 crossings, also known as the trefoil, is a PD of x 1425. Oh no, Probably I chose my initial point differently. So I mean, it's a different representation of the trefoil, but it's still the trefoil. And then the knot with 4 crossings is, and the first knot with 4 crossings is 4, 2, 5, 1, 8, 6, 1, 5. Well, in principle, you can use this information to draw all the knots. And this is a very, very, very long cell because it has 250 knots in it. In fact, the last knot in this cell is a knot that I like to call GST48. Where is it? Oops, here. So GST48 is a knot with 48 crossings. And the reason I care about it is because it's the smallest proposed counterexample to a certain conjecture, which we will discuss later. And therefore, it's particularly interesting to compute its invariants. I mean, of course, the invariants have to be nice and interesting, and we haven't yet established that the Jones polynomial is nice and interesting. But in principle, I care about it, so I've put it in. Anyway, so now that we've seen what is hidden, I should say another thing that's in this hidden cell is when you run it, it will print setting knots to contain all from knot 3.1 to knot 10.165 as well as GST48. And it also imports from the web a certain PNG file, so a certain picture, and prints that picture. So let's see what happens. So let me run this cell, but before running it, I want to close it because I don't want to ever see it open again. Okay, so I run it, Shift enters, run a cell, runs a cell, I'm running it. I hope, here it is. So this is the PNG file, and this is GST48. This is the 48 crossing I mentioned before, and the numbers in blue are irrelevant. The numbers in red are the numbers of the edges for this PD notation. Good. But now let's start with Mathematica. So, sorry, I have to give you a brief introduction to Mathematica before I can show you how to use it to compute the Kaufman polynomial, bracket. So, if you do 1 plus 1 and hit enter, you get a surprise. Okay? I don't know, do you have better exercises to ask, like 2 plus 2? Another surprise. Okay? Do you have any better exercises? Let's do 7 factorial. Okay, so basically arithmetic works as you expect. In fact, you can even integrate. So integrating 1 over 1 plus x squared according to the variable x will give arctangents of x. Now let me enter the trefoil. Here it is. Sorry, it's again. Oh, this is the same convention. Why 1524, 5362? Yeah. Okay? Now let's write a program. So you see, I was using the built-in factorial. Let's write a program to compute factorial. How do you compute 7 factorial? You do 1 times 2 times 3. So you keep an accumulator. Let's call it the prod. And its prod starts with 1. And then you multiply prod by 1, and then by 2, and then by 3, and then by 4, and then you output prod. So you set prod to 1, you do prod is equal to prod times k, for k running from 1 to 7, and then you multiply prod, and then you print prod, and you get 5040. You know, I could copy this thing, paste it again, and instead of 7, run 28, and that will compute 28 factorial. Okay. The next thing is substitution rules. Sorry, am I okay? Am I good? So, if you have a Mathematica thing, and you apply to it a substitution rule. So a substitution rule is 9 arrow 23. This means replace 9 by 23. Slash period means apply a substitution rule. And hence my use here, even in Mathematica, even in the context of mathematics, I sometimes use Mathematica notation. This is apply a substitution rule. So we apply the substitution rule 9 to 23 to the list 10, 9, 180, 26, and the result should be 10, 23, 100, and then 180, and then 26. So let's see if that's what we get. Good. Substitution rules can be more complicated. So substitution rules can include patterns in them. So an underscore means like dot in mathematics. You know, when you write in mathematics f of dot, which kind of means f of something, but you're not bothering to specify what. So that's an underscore in Mathematica. And then if you precede this underscore with a letter or with a symbol, then it means something, a pattern, anything called y, which you will name y. So I'm taking this list 10, 9, 180, 26 and apply to it the rule. Anything called x will be replaced by x squared, or anything, so any pattern which is called x to be replaced by x squared. So I should get, what is 10 squared? 100. 81 beats me. Okay, so let's do it. Well, looks good. I mean, I'll have to trust the computers that 180 squared is this. But you see, it doesn't, the things to which you apply the rules don't have to be numbers. They could be anything. So I could use numbers and then just put a symbol here. The symbol is tembel. Tembel in Hebrew means idiot. Silly. I don't know. It doesn't matter, okay? So I do it, and I'll get tembel squared. Mathematica doesn't know what tembel is, so it just writes tembel squared. Okay? By the way, I could have done even, well, it could have been anything. I could have done something more complicated. So instead of tembel, I could have put tembel plus silly, and I'll get silly plus tembel squared. Sorry, plus is commutative and s comes before t. So Mathematica orders them in lexicographical ordering. You know, I could then use the Mathematica command expand. So if I will expand all of this, well, tembel plus silly squared is equal to silly squared plus 2 silly tembel plus tembel squared. Okay? Good. Now comes somehow the key, the key to the program. No, one of the keys to the program. So I need to somehow implement this relation. You know what? I was meaning not to erase it, but okay, fine. Let's erase it. So I somehow need a names for, I already know how to name this. So basically, if the numbers here are I, J, K, and L, I need to, then this will be named X, I, J, K, L. But now I need a name for a smoothing. So I need to know how to name a thing like this which starts with edge I and goes to edge j, and L and K, okay? So the name will be, so really I will be naming this point, and this is the point which connects I to j. Or said differently, it's a path from I to j. So I will name this P Ij P KL. Likewise, I will name IJKL, I will name this PIL PJK. And so, the Kaufman bracket rule, the key to the Kaufman bracket is every place you see an XIJKL, and now I and J and K and L are named patterns. So they can be anything. 1, 2, 3, 4, 28. So every place you see this, replace it by A times Pij times PKL, that's this, plus B times PIL PJK. Okay? And call the result T1. Why T1? Temporary result number 1. So, you get, well, you got PD. So, you know, maybe I should have printed K again. You know, at the beginning I've set K to be the trephone. But since it disappeared from our screen, maybe I should have printed it again up here. Oops, sorry, not K equals, I want to just print it. So, X1524 got replaced by A times P15, P24, plus B times P14, P52. The second X got replaced by this combination, and the third X gets replaced by that combination. But now what I need to do, well, is just to expand, right? If you expand, I mean that's exactly what expand does, right? If you expand, well, sorry, I need to replace PD by a product, and then expand. And then if you expand the product of pairs, you get, you know, if you have 17 sums of pairs, and you multiply them and expand, you get 2 to the 17 terms, which are exactly the 2 to the 17 terms you want. So I want to take T1. I think I've demonstrated just to see how expand works and then how factors work. Anyway, so what I want to do is I want to take T1 and replace the PD symbol that appears in it by the symbol multiplication. So now it's a big product of things. And then I want to expand this. So T2 becomes the result of the expansion. Now, how many terms are here? There should be 8. There should be 8 summands here. So let's check. There used to be a pointer here, but there isn't. Anyway, just scroll. So there should be 8 summands. 1, 2, 3, 4, 5, 6, 7, 8. One of them has b cubed, one of them has a cubed. There should be 3 with a squared b and 3 with b squared a. If you look at it, you'll find. And then, what does the a cubed one stand for? It says there is a path from 1 to 5, and then a path from 2 to 4, and a path from 1 to 3, and a path from 4 to 6. But I need to simplify it. So I have all of these paths, and I need to convert them into cycles. We'll have to do it next time. I'm sorry, this is such a terrible time to stop, but we'll have to do it next time. But you know, maybe I'll just say that at the end, the whole program is that long. So you apply the first Kaufman rule, you expand, you contract paths, you apply the second Kaufman rule, and you're done. But we'll do it next time. So see you on Friday.